So, welcome to LayerOne Sunday edition. Our first talk is this brave soul who forewent, I suppose, last night's party. This is Karthik Raman, and his talk is Selecting Features to Classify Malware.
Thanks everyone for joining me this early in the morning. My name is Karthik and I work on the Adobe Secure Software Engineering team. I'll tell you a little bit about what my team does. The team I specifically work on is the Product Security Incident Response team, and we're part of the wider security team within Adobe. So we are the public face of security and incident response to the rest of the world, and researchers send reports of vulnerabilities to us, and we analyze these reports and work with the various product teams such as Reader and FlashSpare, to give you a couple of examples. We work with these teams to create the fixes, to verify the fixes. We go back to the researchers who submitted these reports, and once the fixes are good to go, we publish bulletins and acknowledge researchers. And another important project that I'm involved with is a project called MAP, the Microsoft Active Protections Program. And it's a pre-notification program giving vulnerability details to trusted partners. And Adobe joined this program in 2010 July, and we've been active contributors to the content in that program ever since. But the topic of today's talk is something totally different. I wanted to ask this question to start off my talk. How many of you have seen this screen on your machine or on the screen of a loved one? All right. So I'm glad that some of the talks have been scheduled the way they have been. So the audience got a preview of machine learning in one of the talks yesterday, and in another talk there was some coverage of mass malware in relation to botnets. And I'm glad we covered those topics because they're a good introduction to some of the material I'll cover today. And today the objectives are to sort of explain from a high level what the malware problem is, and answer the question from the point of view of a user who sees screens like that we just saw a second ago and ask themselves, how did I just get infected? And the second part is a brief introduction to the application of machine learning to the problem of malware classification. And my secret objective is sort of to introduce machine learning to people who haven't worked in that field, and sort of give you a roadmap of how you could apply machine learning to the problems of malware analysis or other computer security problems, because it's an area that is picking up interest in our community, as was evident from the talks yesterday. Okay, so let's walk through the story. You are a regular visitor to a website, and that website unfortunately is compromised. A couple of months ago, a whistleblowing website called Krypton.org was compromised and was serving up drive-by exploits. So you as a user, you're not too computer savvy, but you use your computer, you browse the web obviously, and one of the sites that you trust is compromised, or you get a link in an email and you click on the link that you don't really know much about, and you're directed to a website that's malicious. Another technique that is used to rank pages and search results higher than legitimate pages is search engine optimization. So whatever the technique, you are directed to a website that is serving exploits. And you're served something like this. You know, you have to spend a little bit of time in a JavaScript debugger to deobfuscate this, and the talk on botnets yesterday covered some of the steps in deobfuscating malicious JavaScript and getting to the point where you can see a legitimate or a malicious URL deciphered from this. So once you did that, you'd be redirected. The user would be redirected to something that looks legitimate but in fact is malicious. So, you know, if the user were to inspect the start of this URL, he'd think that he's going to Google Analytics website, but I've truncated the end of the URL because it's malicious. And he or she is routed through a series of fast flux networks. Again, this is a topic that was covered yesterday. So at the end of that chain, when the user is finally served a piece of malware, it could be served something like a keylogger, which is something that installs itself on the user's computer and logs information he types in memory or on a file on disk, and then beacons his information out to the attacker's servers. Or it could be served a backdoor or any other category of malware, whatever the attacker's intent is reached at this stage. So if antivirus that's installed on the user's machine, and consensus is generally that users of Windows computers should have some sort of antivirus installed. At this stage, if antivirus fails to detect the malware that's served by that website at the end of that chain of fast flux networks, that's when the user's machine experiences, in a manner of speaking, a mushroom cloud. Or worse, something like this. If the malware is poorly engineered, it could cause a blue screen of death and make the data on the user's computer irrecoverable. But you all know this stuff. So the equation I'd like to offer as a model for how mass malware spreads and is effective is the combination of mass malware with dated AV signatures leads to mass infections. And the topic that we'll analyze in more depth is the second piece of the equation, which is why dated, what are dated AV signatures and why do signatures get to be dated? So let's ask that question. Why do AV signatures get to be out of date? Well, one example is, one explanation is the malware obfuscation testing and release cycle. So two of the Trojan families that were mentioned in the botnet talk yesterday were SpyEye and Zeus, and as coincidence would have it, I have screenshots of two of those to prove my example. So this is a screenshot of the SpyEye Trojan, and if you purchase a copy of this toolkit, you'd see something like this on your machine. And remember, you're a bad guy at this point. And I'll call your attention to that circle on the screen, which is a field for encryption key. So you as the bad guy, you're setting up a wave of malware infections, and you want to create a piece of malware that's undetected or fairly undetected by the scores of AVs. What do you do at that point? You use an interface like this to specify a custom encryption key. And you're hopeful that that custom encryption key will bypass a bunch of AVs out there. And so if AV signatures in the past are written to a specific encryption key, then they'll miss the decryption of this and detection of this piece of malware because the encryption key has changed. Another source of obfuscation is is indicated by the second circle, which is the packer, UPX in this case. And quickly, for those who are unfamiliar with what a packer is, it's a sheath in which to cloak your malware. Now, packers, like any other technology, have both legitimate and nefarious uses. So if you're a game developer and you want to protect your game from being reverse engineered or make it really hard for people to use your software without paying appropriate royalties, then you might cloak it within a packer. But the malicious use case here is to sheath malware within a packer. So if an AV scanner doesn't have the means of unpacking a specific packer, then it'll be completely undetected by it. So in the SpyEye case, you have both encryption and the use of packers. So step one was adding obfuscation and encryption to the malware. The next step is quality assurance for the malware guys. They may send their samples to a website like VirusTotal. How many people are familiar with VirusTotal? It's a website based in Spain, and what it offers is a score of AV software that you can scan your binaries with. Now, if you're an AV analyst, the use case is you're analyzing a sample and you want a quick preview of what other AV companies detect the sample as. So you may upload it there and get a report of what other people detect it as and what they're calling it. But the bad guys could use it, equally, and to figure out how many AVs out there detect the piece of malware that they're trying to set up and serve via this wave of infections. And in this case, this is just a screenshot of a random sample. It seemed like 28 out of 42 AVs detected this particular sample. Now the bad guys might look at this ratio of detection, or rather the ratio of what is not detected. In this case, it's 14 out of the 42 AVs that don't detect this particular sample. And if that number is too low, they may just go back to the drawing board and say, I want a more effective mass malware campaign, and I'm going to add different kinds of encryption or different kinds of packing or layers of packing in order to make my malware more effective and infect as many computers as possible in the first run. And this is a screenshot of the Zeus or Zbot Trojan. And if the malware guys were unhappy with that step of QA, quality testing, of how many AVs detected their piece of malware, they'd go back to this step and add different kinds of encryption or packing. Polypack is a project by Oberheit et al. And the point I'm trying to drive home here is that in addition to using a single packer, you could multiply the effects of what a packer does to make AV ineffective by adding more and more packers and layers. Now I'll pause for a brief minute and let you guys read the abstract of that. So if the effect of a packer is to make the job of an AV less effective, then you can multiply that effect by adding layers of packers, and that's what this project does. Now, this is an academic project, and the results are published, and the methodology is published, but it doesn't strain the imagination to say that the bad guys could have custom setups like this, and as part of their QA testing, and once they have a string of packers added on to their malware, that's when they're happy with it and release it. In summary, the malware obfuscation testing release cycle begins with a toolkit that lets the malware guys add encryption and different kinds of obfuscation. They pass it on to the public AV scanning engines such as VirusTotal, or use things like Polypack to add different kinds of layers of packing. And if they're unhappy with how many AVs detected, they'll go back to step 1 and change up the encryption or obfuscation. Once they're content with the level of detection, they'll serve it in a mass malware campaign via infected web pages and drive-by exploit downloads. And once that wave of infection is successful and AV catches up with the lag, they'll go back to step 1 and start another campaign of mass malware. So that's a vicious cycle for mass malware. And from the point of view of the user, the user doesn't care about all of this. What he or she suffers is this, unfortunately. These are screenshots of malicious programs that pretend to be legitimate. And these are actually screenshots from the Microsoft Malware Protection Center blog of fake antivirus or ransomware programs. The user who doesn't know better believes or is connived into believing that these are legitimate programs. If they pay a $50 or something license fee they'll get rid of the infection. But these programs do nothing but scam the user. So the point of discussing all of that is this thesis is that for malware, the software development lifecycle outpaces that of antivirus. And in a lot of cases, this is economically driven. The malware guys make a lot of money from doing this, and somewhere that's part of their motives and impetus. And the antivirus industry is slow. So the natural question to ask at this point is, well, how can we make AV more current? How can we make the job of AV more effective? And then surveying the research in this, an automatic answer is, well, you've got to automate everything. And research discusses things like static detection, which is detecting malware for what it looks like, detecting malware for what it does, dynamic detection, detection in the cloud, so detecting certain features of malware or the preponderance of a certain hash of malware. But is there anything else that we can do? I'm glad the speaker badges look the way they do, because they remind me of the Cylons from Battlestar Galactica. And it's just a coincidence, because we need the Cylons from Battlestar Galactica on our side. We need machine learning. The machine learning is the process of extracting useful knowledge from masses of data. So we're transitioning into part 2 of the talk, which is defining more terms and building up our knowledge towards how we could apply machine learning to help classify malware. So let's define a virus briefly, because it's a term that is thrown about easily, and maybe some people don't know the original definitions. Fred Cohen, who wrote the first computer virus and was one of the original researchers in the antivirus field, defined a virus as a program that can infect other programs by modifying them to include a possibly evolved copy of itself. Now, some people complain about this definition, that it could also apply to general purpose programs such as compilers. And Peter Zor, who's another eminent researcher and one of the earliest researchers in the industry, redefined a virus as a program that can recursively and explicitly copy a possibly evolved copy of itself. And this is the most widely accepted definition of viruses today. So let's take a quick trip down memory lane, computer memory lane, that is. This is a screenshot of one of the original computer viruses called Brain. And the interesting thing about Brain was that the address of the people who wrote the virus was embedded within the machine language code of the virus. So Brain spread via floppy net, sneaker net, and it would, you'd have to insert a floppy disk in the machine that had Brain on it. It would copy itself onto the disk, and you'd walk over to another machine, and you'd spread Brain like that. Now, Mikko Hipponen, the CEO or CTO of F-Secure, did a TED Talk some time back in which he looked at the assembly language of Brain and asked himself the question, so do these guys still, the guys who wrote this virus, do they still live at this address? And he actually went to this address and knocked on their door, and yeah, lo and behold, they were still there. So I'll give you a link to that TED Talk at the end of this talk. It's a pretty neat anecdote. From spreading via sneakernet or floppy net, worms or viruses evolved to spreading by exploiting operating system vulnerabilities, and these are all broad strokes in the evolution of malware, by the way. So when I went back to my college campus at the end of the summer of 2003, the entire network was down. I was curious and went to the IT department, and they said, yeah, we're getting hit by the MS Blaster worm. So that's my personal relationship with the MS Blaster worm, not being able to use the network. But if you looked at the machine language code within MS Blaster, virus writers actually tend to do this a lot. They'll put in English language messages, and they'll plead to the virus analysts to use a particular name for the virus, and we just ignore that stuff, but it's interesting to share. But the writer of MS Blaster put in a message to Bill Gates: why do you make this possible? Stop making money and fix your software. And they did. They passed it within a couple of weeks. So in addition to being the device used by the Greeks to besiege Troy for computer viruses, a Trojan horse is what we've seen so far. It's a program that pretends to be legitimate, but in fact does something bad or does nothing at all, but scam the user. Okay, so we're almost completely done with part one, and we're doing very good on time. Any questions so far about part one? All right. So we're going to look at machine learning for malware classification. More definitions. The scope of the research was classification of polymorphic malware, particularly. What do I mean by polymorphic? A piece of malware has multiple variants and does not affect other programs. You may call a virus that mutates or evolves an infector, and you may call a virus that mutates and changes its shape. You could call it metamorphic. So those two categories of viruses were out of scope for my research. And examples of what is in scope are backdoors, which are programs that run in the background, collect information, and beacon that out to the attacker servers. Downloaders, which download other programs and let the user have a presence on your machine. And one of the tools that the attacker could download on a machine is a RAT, a remote administration tool, which lets him run commands on the machine and perhaps like control a botnet or something like that. Yeah, infectors and packers are out of scope too. The objective of a packer is to make one binary resemble another as much as possible. So if a binary contains sections that are low in entropy, the objective of the packer is to make the sections within the binary as high entropy as possible. And that's a more difficult problem to address using machine learning than trying to classify files that were originally not packed. So that's within the scope of this research. Okay, so why is polymorphic malware important, and how much of it is out there in relation to the other categories of malware? This is a screenshot from a couple of weeks ago of what percentage of malware detected, what percentage of malware out there is Trojans, which are polymorphic, as opposed to other categories of malware, and it's something like 80%. A little more amplification of what I mean by polymorphic. This is a family of termite, species of termite. On the left is a king termite, A. B is a queen termite. C and D are secondary and tertiary queens. E is soldier termites, and F is a worker termite. Now these are all the same species, but they don't look the same. They're dissimilar in appearance. But it doesn't mean that we have to classify them differently. So polymorphism is the labeling of one thing as one species, regardless of how they appear, because their function is the same. They're all termites. They do similar things. There's polymorphism in Battlestar Galactica. How many Battlestar Galactica fans here? All right. The Cylons are all polymorphic. They have similar purposes, but they look different. So say you achieve classification. What are some of the other steps that follow in the methodology for analyzing binaries for antivirus analysis? The next step is clustering. So you classify malware as malicious or clean, and for the files that you classified as malicious, the next step is to assign families. That's what's meant by clustering. Going hand in hand with clustering is something known as detection. So this is the most commonly used term for antiviruses. Antiviruses detect malware, but what's going on behind the scenes is the clustering has happened and classification preceded that. And if your system has already been infected by a piece of malware, then after you detect it, the antivirus is supposed to delete it and clean up any other remnants like registry keys or remnants in memory so that the malware doesn't respawn on reboot, and then delete whatever else is left on the system. So at a high level, that's what's involved in antivirus scanning and cleaning. So in the course of the research, there's a lot of similar research, and I wanted to give you sort of a preview of this stuff. So if you're interested in it, you could look it up easily. Riek et al., a group based in Germany, they mined malware behavior based on sandboxes. So they collected sandbox logs and used those logs as features to feed into machine learning algorithms. So in general, this is the machine learning approach to analyzing or classifying malware. Two groups separately used a search engine method to try to classify malware. So they looked at the contents of the malware and they added it to a search engine database. And when an unknown binary came by their way, they'd extract similar features and do a search engine sort of lookup. So when you search something on Google, it does a lookup of a corpus of data, whatever is similar, cosine similarity method, for example. And that's what they applied to the problem of malware classification. For malware detection, another group used a technique from biology known as phylogeny, which is a term that means building up a family tree of malware. And once you applied this technique, the malware would already be classified and within a tree that was indicative of its malicious nature and whatever appropriate category it belonged to. Another technique was the use of n-perms. N-perms is the permutation of an engram. Is anyone familiar with what an engram is?
No.
Would you mind defining it?
It's when you have patterns of like usually context of multiple strings in a row, and like a 3-gram of 3 strings, and you can find patterns.
Cool.
Other larger bodies.
Cool. So, thank you. N-grams are exactly that. They come from linguistics, but you can apply that concept to malware. And you can basically say, I'll define a unit to be 1 byte or a series of bytes, and a sequence of those units becomes an n-gram. And if you permutate that, in which you don't care about the order in which those units appear, that's an n-perm. So they use a technique like that to build a phylogeny, and it was an application of both machine learning and the search engine approach. A different approach was using the control flow graphs within the binaries of malware to derive a fingerprint of the malware. And this is a geometric or structural similarity approach. A different group did something similar. They looked at control flow graphs and basic blocks and also used machine learning or search engines. And there's a lot of theoretical research also in how to normalize viruses. So people define use formal logic, formal methods to specify the syntax and semantics of what's contained within a binary, and then if by applying normalization methods, binaries that are similar would be more and more similar, and binaries that are different would be more and more distant, and then they finally use a clustering method to sort of put that malware in the same families. Okay, so that's a broad strokes overview of what's going on in detection. In clustering, fingerprinting is also a common method that people use, and Brumley and Zhang and Wachurski both published fingerprinting algorithms for clustering malware. So if you're doing this for fun or you're doing this for your job, you could look up their papers and implement their algorithms for clustering. And a group based in Spain used distance algorithms to find similar malware. So they project, they put malware into Euclidean space, and similar malware will be close to each other in that space. And Bayer et al., another group based in Germany, again used machine learning, and they derived a behavioral profile of malware, and this still is actually available for anyone to use. It's called Anubis. So now that we've looked at all the strategies out there, I wanted to give you the methodology that I followed to use machine learning to apply to classification. The first step is to extract features. Then you train the models using the features you extracted, and the models would generate classifiers. If you're happy with the results of the classifiers, you'd use them to classify unknown files as 0, which might be clean, and 1 as malicious or dirty. And in the beginning, I started with 600 features derived from a binary file. So what is a binary? What do I mean by binary file? The majority of systems out there are still 32-bit, and the exe and DLL are portable executable file formats for 32-bit systems. This standard is public. You could go to the Microsoft website and download the standard. I wanted to give you a preview of what this looked like visually. This is a tool called File Insight, and it has a P parser built into it. So if you open a binary within that, it would show you the structures within a particular P file, and this is a section of the P file from the P header. The P also contains sections within itself, so .text, our data, resource, these are all sections. It also could contain imports, so what it uses from the operating system's API, that's what I mean by import. And DLLs might also have exports, so there's a functionality programmed into the DLL, and another program wants to use it, so that's what's meant by an export. And this binary doesn't have exports. A little more about what I mean by features. This is the primula flower, and the picture on the left and the right are both primula flowers. So feature 1 is the corolla, feature 2 is the calyx, and they're both in the same place in both these flowers. But feature 3, the stamen, is in a different place, and so is feature 4. Do features 3 and 4 make these two different flowers? No, they don't. They're just in different positions. And why are they in different positions? The function of polymorphism in biology is to let the species be more robust in the face of adversaries and predators. And a similar logic can follow for polymorphic malware. Why do the malware writers introduce polymorphism into their malware? They want their malware to be more robust in the face of detection by antiviruses. So another nuance that I had to explore in this research is why might fewer features be better than more features to feed to machine learning algorithms? And at first, it's counterintuitive. You'd think that the more data you supply to your problem, the better results you'd get. Actually, that's not true. The textbooks on machine learning tell you that irrelevant features actually distract the machine learning algorithms. And by using the appropriate features, you can improve the performance, you can represent the problem better, and it also helps the user because they aren't distracted by the irrelevant features. So back to the example of the primula flower, if the base of the flower had been used as a feature to separate something as a primula versus something that wasn't, it's no use at all because it's the same in both the examples of the primula. Here's the research that was most relevant to the stuff I was doing. The reason I pointed out is that a lot of people had achieved very good accuracy in the results, and as I was trying to think of what are the questions I could try to pursue, it seemed like there were two key questions that were still unaddressed by the existing research. And the first of these was which features could be used in machine learning for classifying malware, and why? And a related question was what are the minimum features for good classification? So a lot of this research would take all the features available or predefined set of features, but not focus on minimizing that features to figure out what set of minimum features were necessary to classify. And I was able to actually derive excellent classification using just 7 features for that data set. And how this could be used is it could be an existing layer to antivirus technology. But doesn't mean the end of it. You know, we still need unpackers and deobfuscators, and all the other stuff that are currently part of antivirus technology. So how did the system look? You have a data set, which is your corpus of malware and corpus of clean files, from which you extract features using a parser. This is fed into a classifier, which is a machine learning algorithm, which has been trained to identify something as malicious and something that's clean. So when you're training these classifiers originally, you want to evaluate them. So you take the model that comes out of the classifier and you evaluate it for what the false positive rates are, what the accuracy is, and so on, other metrics. And if you're satisfied with the evaluation, you may take that model and use it within another testing system. In the beginning, I started with for my parser, I started with a tool called PEDump, which is a legacy tool for parsing the P file format. And later, when I distilled this research to a tool that other people could run, I used the P file Python module, which is it's an open source module. What is my data set? It was 100,000, a little more than 100,000 pieces of malware from the VX Havens website. If you've been following the Twitter sphere and news, a few months ago this website was actually shut down. So I did this research in good time. The 16,000 clean programs came from base installations of Windows XP and Windows 7. I started with 645 features initially, features extracted from properties of the P file format. And some of the features I had to calculate. So machine learning algorithms, they tend to accept a certain kind of feature. It could be all numeric, all nominal, or all binary. I decided to go with numeric features because that seemed to represent most of the data within a P file. And so some of the calculations had to be whether something contained an import or whether something contained an export, for example. So that's what I mean by calculated features. And Matt Petrick's article, it was very insightful and helpful in my analysis. For the classifier and evaluator, I used an open source Java project called Weka. And if you're starting off with machine learning, I'd say this is absolutely the place to start off with because it dramatically cut my learning curve about machine learning. So there's a lot of algorithms in machine learning that have been implemented by this framework, and it's really awesome because it's also scriptable. So you don't need to use that GUI. If you figured out what your objectives are in deriving a classifier, you could just simply tell Weka to run that classifier on your data behind the scenes. So I ran 6 numeric machine learning algorithms on my data. I started with 645 features, and in the second experiment with 100 features. And I also ran these classifiers individually against particular features, and I wanted to check the classification. So these are the results, and some of these features had pretty high accuracy. But wait a minute. Do you know who that is from Battlestar Galactica? Leoben. Leoben. Check the classification. Some of these features individually had really, really high accuracy. And that was staggering because, in theory, you could use just one of these features to separate malware from clean files for that data set, and you'd have an accuracy of 92.34%. Okay, so to answer the question, is it possible to derive a feature set that's as small as possible instead of using all the available features? How could I go about that? I went about grouping the P structure headers into buckets. Created 7 buckets based on the portions of the P file. And the algorithm for deriving this minimum feature set went something like this. I started with just one feature from the first bucket. I ran all of the algorithms I was interested in running. Then went to the next bucket, took the best feature from that bucket, and then ran the 6 machine learning algorithms with those 2 features. So I continued this process and noted my results for 1 through 7 features. When the 7 were done, I went back to the first bucket and took the next best feature from that bucket, and then continued. So I ran this for 13 iterations, so all the way to 7 and then back to 13. And if the question that is it possible to derive a minimum feature set for good classification of malware could be answered, then I should have seen an inflection point in my results after a certain minimum set of features were met, after which the results were just similar and the gain in accuracy was minimal. And indeed, that was the case. So these are results from instant base learner, one of the machine learning algorithms I use. And here you see after 7 features, there is an inflection point, and the gain in accuracy is not as dramatic as the gain in accuracy all the way through to the first 7 features. Similar results for the J48 classifier. So the J48 graph, inflection point at 7 features. Similar for part. Seems like there's an inflection point at 6, but for consistency, let's just say 7. Similarly for random forest, rider. Okay, so then I took just these 7 features and used them as the sole inputs to the classifiers. And with just those 7 features, it seemed like I was able to derive a really, really high accuracy in classifying malware. So there was a 98.21 accuracy, and the false positive rate was really high. So, if you're doing this commercially or if you're doing this in a production system, you probably should not use machine learning algorithms right out of the gate without optimization and tuning. But it's still great. I mean, we got a 98.21% accuracy for 130,000 pieces of malware with just 7 features. So you may ask, how did these 7 features individually or in combination work so well? Well, it seemed like they were picking, the machine learning algorithms were picking the features that were separating malware from clean files immediately, and then adding the other features in nominally. So if we, in our manual analysis, picked the 7 features in our data set that separated the 2 classes of data the best, then we wouldn't need to worry about collecting the data for other features and distracting our machine learning algorithms. And for my data set, these were the 7 features. You can read them on the screen, but if you're familiar with analyzing the structure of binary, you might recognize some of these. Debug size denotes the size of the debug directory table. And one explanation, post hoc, just because we don't have the data to back it up. One possible explanation post hoc is that this is a good feature to separate malware from clean files, because only Microsoft-related executables, not even DLLs, had this feature populated. And none of the malware that was in my data set had any value set in this field. So immediately that was a good feature for the machine learning algorithms to separate clean from dirty. A similar logic applied to image version, which denotes the version of a file. And only Microsoft-related binaries had this value set to something that was non-zero, and all the malware that I analyzed had nothing in here. So in my calculations of those feature values, I just set this value to 0. So how might you use the models that you generate from training your classifiers? You have an unclassified P file, you feed it to a parser, the parser feeds the data to a model, and the model gives you a result, basically, input and output. You could plug all of this into existing AV infrastructures. On the desktop, you could use it to consolidate signature databases. So you have a trove of malware that you want to detect and classify, and if you have a huge signature database, you could run machine learning against this database and derive a compressed model that captures what that malware is. In the cloud, you could be more aggressive with the rate in which you run these algorithms. You could use it to quickly detect mass malware as it's spreading across computers. On the gateway, perhaps you could use this most aggressively. You could actually prevent worms from spreading by applying some of the models that you train. So I distilled a lot of this research into a quick tool. It's called Malclassifier. It's on SourceForge already if you want to take a look at it. The objective of that is to share this research with the community and sort of help you guys build on it. It's an open source license, so you can build on it at will. In closing, I'd say that if you're interested in machine learning for computer security in general and malware classification in particular, please start with Weka, because you'll save yourself a lot of time. I was faced with either coding the machine learning algorithms myself or using Weka, and you can imagine how much time I saved by using Weka. There's a book that accompanies Weka. It's not free, but I highly recommend it because it uses Weka as its teaching model. And the publishers did a neat thing of giving an example of what machine learning is. There's a big cat in the weeds, and it sort of exemplifies the definition of extracting useful knowledge from raw data. So I've actually been asked this question before, and to anticipate what some of you may ask. So I just talked about 7 features that separate malware from clean files from my data set. if there's a malware author out there who reads my paper and says, I know these 7 features and I'm going to program my malware so that those 7 features fall, the values of those 7 features fall within the parameters that I expect to find for clean programs. And the answer to that is, yeah, sure, but it doesn't really change the nature of the arms race that's already existing. And that thing is a quote from the book. The bad guys can also use machine learning. Well, as with any science or technology, both the good guys and the bad guys can use the same things. But can the human analyst benefit from using machine learning? I think so. Can anyone here tell me which of these 2 is a projector lens and which of these 2 is a camera lens? Anyone want to take a guess?
One on the left is a projector.
One on the right is a camera.
Rubber.
Cool. Thank you. Would you agree that it's sort of a hard question to answer? So the point I'm driving at is the technology to project light and the technology to create light is to capture light is very similar, and the analogy is the technology to write viruses and the technology to detect viruses will also resemble each other, and so the bad guys can use machine learning, but I think it can buy the good guys more time. And when we're faced with like tons of malware coming out every day, by using machine learning algorithms that self-train and self-correct, the human analyst could be focused on the more longer-term research and more important questions that is less taxing on them. Another thing that the AV industry gets hit a lot with is a high-profile false positive. Now, I couldn't say what your business, how your business assigns costs to what false positives and false negatives in your technology are. But the neat thing about machine learning is if you have a value to plug into these equations for machine learning, that could be one of the inputs used to train your classifiers. So you could have a classifier that's attuned to your particular business problem. And everyone's calculation there is going to be different, so I can't tell you what it's going to be. A final note is to please consider the privacy of the user. If you're running this machine learning infrastructure for detecting or classifying malware in the cloud, and you wantonly extract features from developers' machines, for example, you could be extracting things like strings from developers' machines which leak intellectual property into the cloud, and if there's a breach, then we know what a particular company was working on. To that, I'd say there is research on privacy-preserving data mining. It was actually out of scope of the textbook I referred you to, so if you're interested in that, please look up the research in that field. This is the research I alluded to that was most close to my own research. If you're interested in this stuff, please do read this. This is the TED Talk I talked about, where Mikko Hyppönen goes to the address in question of the guys who wrote the brain virus and has a conversation with them. And my thanks to these references for images and content. So I'm going to leave you with, I'm a Battlestar Galactica geek, I'm going to leave you with my contribution to the problem of classifying Cylons in Battlestar Galactica. So if you don't watch the show, towards the end of the show, your objective is to classify who is a Cylon and who is a human, because the Cylons resemble humans. So you don't have 4 seasons to catch up. I'm going to give you 4 Cylons here. It's not all of them. It's not all of them. And I'll tell you that my classification has a false positive rate of 20%. So you'll just have to watch the show to correct it. That's it. So that's my email address if you have any questions. And the tool that distills some of the research I did is up on SourceForge. It's an open source project. That's it. I'll take any questions.
Early on, you said a site in Spain, which I heard is Varstotal.
Varstotal.
How do you spell that?
Virus, V-I-R-U-S, T-O-T-A-L. Yes, sir.
So previously, did all your good programs were from Microsoft Windows installation?
Yes.
Are you concerned that you're just discerning between a Microsoft product and other?
Sure. So it's always a concern in machine learning to overfit your models to your data set rather than solving the general problem. So that's a valid concern, and my constraints were the availability of clean programs and whatever dirty programs I could get my hands on to sort of like prove or disprove this hypothesis. And the hypothesis was, yeah, it's possible with a few features to separate clean and dirty. So if you reapply this research, you'd have to use different programs and sort of use more files to make it generic to the wider problem in the wild. What else? All right, thank you very much.